For our Physics 212 project, we are going to be covering the billiard ball problem. I'm Darren, and my group mates are Connor and Alexis. What is the problem we are trying to solve? Well, there's a billiard ball that's going to be struck by a cue in a direction parallel to the table. The ball is going to roll across the table. And we're trying to find where the ball should be hit such that the ball will roll without slipping. We want to find how fast the ball will roll. We also want to find the translational and rotational motion if the ball is struck in the middle. Well, we also want to find how far the ball travels before it rolls without slipping. We also want to find, well, first, we have some variables. There's the mass of the ball, represented by m, radius by r, force that the ball is hit by Fs, time passed by delta t, linear velocity by v, angular velocity by omega, linear acceleration by a, angular acceleration by alpha, and what we want to find, h, distance between the table and striking point. We have some assumptions that the ball is going to be hit harder than the friction between the ball and the table, and we're assuming that this takes place on Earth. Some principles that we can keep in mind while trying to find our end goals is Newton's second law, first of all, that acceleration is going to be equal to force divided by mass. There's also the moment of inertia of a sphere spinning about its center. It's going to be equal to 2/5 times mass times radius squared. There's going to be the angular acceleration, which can be found by torque divided by the moment of inertia, which we know above. There is, of course, the definition of velocity, which is going to be acceleration times time. Then there's omega, which is going to be equal to v/r, velocity divided by radius. In order to find where the ball should be hit, we want to find where the ball should be hit such that it will roll without slipping. And in order for it to roll without slipping, we had to create a perfect rotation where the torque generated by the force must balance out with the frictional force, such that it experiences both translational and rotational motion. And this can be done by hitting the ball at its sweet spot, which we find out is located above the center of the ball. How do we find this out? Well, we have a few equations here. There's the radius, the mass, and what we want to find with all of this work is c, the height from the ball from center to striking point, represented by c. And in order to find h, we can do r plus c, which will be the radius plus the height from the center to striking point, which is what we want to find. We have a few equations here, which is that torque is going to be equal to the force the ball is hit times c. We can replace this. We can equate this to a moment of inertia times omega divided by delta t, which is going to be equal to mv/delta t times c. We also have the moment of inertia here, and then we also have omega, and we can plug both of these into here, and we can equate it equal to mv/delta t times c. So once we plug in the moment of inertia and omega, we find all of this. And to simplify, we know that we have m on both sides, we have velocity on both sides, we have delta t on both sides. We can get rid of all of that, and then we can combine the radiuses such that we end up getting 2/5 of the radius. So we can add c, 2/5 of the radius, plus r, we end up getting h, 7/5 of the radius. And as we can see, the ball, 7/5 of the radius, is going to be just above the center of the ball, where that's where we want to hit it, such that it will create rolling without slipping.
Now that we've looked at that perfect spot of where to hit the ball so that the rolls without slipping, we now want to see how fast the ball rolls when that happens. And so with that, we're going to look at our equation, and we can see that force from the pole cue times the time that we're given equals mass times velocity, or our speed. And with that, we can easily rearrange this equation to give us that speed of the ball. And that's going to be that the force from the cue times the time divided by mass is equal to the speed. And so with that, if we want to look at the angular speed, This is going to be pretty easy because we know that we're rolling without slipping. And so we can use the equation omega equals linear velocity over radius. And so we're just basically going to divide our velocity by radius. And so that's going to give us that angular speed of the force times time divided by mass times radius. And now that we've looked at what happens when it's struck at that nice sweet spot, we can look at how motion looks and how distance traveled is like when we're struck in the middle of the ball. And so what we're going to look at is taking into account our initial velocity and initial angular velocity. We can look at our linear impulse equation and also taking into account friction. As you can see, I have this free body diagram on the right. And with that, we can see that our normal force and our gravity force are going to cancel each other out. They're a couple. And so knowing that friction is equal to our friction constant times normal force, we can rewrite it to have that normal force instead be our mass times gravity or our gravitational force. And with that, we can write out our linear velocity when struck in the middle, and that's going to be that initial velocity of the ball minus the friction constant times gravity times time. And then we looked at linear motion, we can look at the angular motion and how that relates. And so we're going to want to look at that angular acceleration, and again, accounting for friction once again. And we're going to get an angular acceleration of our friction constant times mass times gravity times radius divided by our moment of inertia of the ball. And in that case, it's going to be 2/5 mass radius squared. And with that, we can find the angular motion, that angular velocity, and that's going to be that our angular velocity is equal to our initial angular velocity plus 5 times our friction constant times gravity divided by 2 radius times time. And now that we have that motion set out there, we can look at how far the ball is going to travel before slipping stops, before motion becomes nice, perfect rotational motion. So again, we can look back at that equation and we can set it up a little bit differently. So now that it's linear velocity equals radius times angular velocity. And so we know that the slipping is going to stop when that equation rings true. And so if we plug that in, we can find that time frame we're looking for before that equation rings true. And that's going to be from time 0 to time equals 2 times the force from the cue times time divided by 7 times our friction constant times mass times gravity. And now that we have that time frame, we can easily figure out how far is traveled during that time before the slipping stops. And so we can go back to what we talked about the linear motion, and we can look at the linear velocity and plug that time frame in, and that's going to give us our answer. And we're going to find that distance moved before slipping stops is equal to 12 divided by 49 times our friction constant times gravity times the force by the pole cue times time divided by mass squared.
Now that we have found our equation for the distance moved before the slipping stops, we can now talk about the units. So for our equation, we have S right here is going to be for meter. The units are in meters, and then our time is in seconds. And then we have this F of S, which is calculated in newtons. And then our mass right here is going to be in kilograms. And then we have G, which is the constant for gravitational acceleration, which is in meters per second. And then we also have the kinetic friction coefficient, which is unitless for this. Now we can go over the covariational reasoning. So to make sense of this, we have distance right here. And then we have, it's split up into technically 2 different things with parentheses right here. So I kind of like split it down right here. So we have two constants right here. So this is going to be whatever. This doesn't really matter for this covariational reasoning. So we have our force, time, change in time, and then our mass. So if the force were to increase, the distance traveled would increase because it is on the numerator side. So when you multiply, let's say you have a larger force, same mass, same time, bigger number means it's going to be greater. So the distance would be greater since this will stay constant the entire time. But the same thing goes for time since that is on the numerator. It's not being divided. It's the if this mass is staying constant, then and you have a bigger number here, then obviously you're going to get a bigger number since this is also being squared. Now is the opposite for mass since mass is in the denominator. So if we keep force and time the same, but the mass were to increase, then it would be a smaller number because if you have a bigger number on the denominator, it's going to start to go down, especially since it's being squared. For our special case, it is true under the assumption that the mass and friction coefficient are not equal to 0, which is, and this is because if either of those two values were to equal to 0, then it'd be undefined because there'd be a 0 in the denominator. And in this case, or in the case that force is equal to 0, then the ball will simply not travel any distance because if you have a 0 times something divided by something, 0 divided by anything is going to be 0. Then you square 0, still 0. Multiply this by 0, you're going to get 0. The ball will not travel if there is no force. So, to conclude, from the equation we found, we can conclude that the harder the ball is hit and the longer it travels, the further the ball will go. Simple. This is because if there's more force, then it's going to travel a further distance, given that we're keeping mass constant. So you give more force, it goes further. The opposite is true for mass, though, because if you have a greater mass, but you use the same amount of force, it's not going to travel as far once you factor in the kinetic friction coefficient and then all the other stuff with force and the change in time. For our reflection, we said that the billiard ball situation it's not dissimilar to some problems we did in 211 where we predicted the distance based on force exerted, but we also have done some problems in 212 relating to the translational angular velocity that we did in studio and lecture. One example is in week 3, we worked on a hula hoop and how it rolls without slipping, which is similar to this because we're figuring out not slipping. So both of these problems dealt with perfect, in quotations, perfect rolling motion and involved the use of the equation angular acceleration is equal to velocity over r. And just some image sources right here to show you where we got our stuff from. Yeah.